Hi everybody, welcome. Thank you for coming. Welcome to our talk about plugging into the Java compiler. I'm Éamonn McManus and this is Christian Gruber. So a quick note about who we are. So I've been at Google since 2011. I was at Oracle before that. And I'm working on this as part of my 20% time, which is one of those Google...
Whoop.
That's not me. That's not my slides.
Yeah, we have the wrong slides up.
Okay, I'll stop talking now. So we have a bit of an AV problem, but it's okay because I'm only talking about myself and the slides aren't all that interesting. I'll keep talking and hopefully this will be sorted out. I am the author of two annotation processors, or three annotation processors, AutoValue, which I'll be talking about, Annotation, which is kind of a variation of that, and the JavaFX builder generator, which is now obsolete, but in the first releases of JavaFX, the Java version of JavaFX, there were builder classes, and they were produced by an annotation processor. Okay, over to Christian.
Hi, so I'm a Googler as well. I've been with Google since 2009. I was part of a test mercenary group, which has been blogged about by one of the former test mercenaries. Won't talk about that. Right now I'm part of the Java core libraries team. You'll probably know them as the group responsible for Guava, but my focus is on Dagger, which is compile-time dependency injection, and I'll talk a little bit more about that. Also formerly Oracle and Sun way back in the 90s. And apart from having done annotation processors with respect to Dagger, I was also part of AutoCommon, a set of tools that we'll talk about a little bit, and I was part of creating the truth assertion testing library.
Okay, so outline of the talk, we'll be explaining what an annotation processor is. We'll be giving a couple of examples, AutoValue and Dagger, which respectively we've worked on. And we'll be telling you how to go about creating your own annotation processor with some tips and tricks. So, quick reminder what an annotation is. Presumably everybody knows this, but just in case, it's that at thing that you put on various elements of your program, like on a class or a method or a parameter, or as of Java 8, a type. So an annotation processor then is basically, so the title of the talk is plugging into the Java compiler because it's a way of extending the Java compiler with your own code that runs during compilation. So this is a standard part of the Java platform. It was standardized by JSR 269 and it's been available since Java 6. But it's really only beginning to take off in the last couple of years, I would say, with improved tooling and a number of annotation processors that are kind of showing the way. So it is a standard. It's supported by the two major Java compilers, JavaC and ECJ, which is the compiler that Eclipse uses. And so an annotation processor is something that you put in the compiler. It can see the code that's being compiled. It can potentially introduce new errors or warnings, because it's doing additional analysis beyond what the compiler will be doing. And it can also generate new Java code, which itself will be compiled, and that's what we'll be seeing in detail. So here's an example, AutoValue. So to explain the problem that's being solved here, a value type is a class which is basically just the sum of its properties. It's an immutable class, it has a bunch of properties, and one instance with a certain set of properties is equivalent and interchangeable with another instance that has the same values for its properties. So immutability is good. I don't think I really need to explain why that's so, but you end up, if you're writing an idiomatic Java program, you typically end up with a lot of these value classes, and as we'll be seeing, there is a certain amount of boilerplate that's involved in doing that properly. So examples of where you use this, you want a tuple basically, you want to return several values from a method, or you want to have a map key that's a complex value, or a map value that's a complex value. But you don't want to be using tuple because that's really untyped. It isn't actually telling you what the members, the properties actually mean. So here's an example of a value type, right? So it's a class address that has just two properties, which are street address and postcode. And here's the ideal way that you would write it in Java, and we'll see that this doesn't really work out, but you would like just to be able to say, okay, I have these two fields, street address and postcode, and I have a constructor that initializes them. So that is a thing that you can write. It works, but it's not great, and we'll see why. So first of all, one thing is that you don't generally want to expose public fields like that because you're binding details of your implementation into clients. So every client of your class knows that you have these fields and you can't ever change those fields without changing all the clients. So instead of doing that, typically what you do is you add accessor methods, getters. So here we've added a street address method and a postcode method, and that's great. Now we have private fields and we have a proper interface. But it's still not perfect because we haven't defined equals and hash code, which means that if we want to use one of these as a key in a hash map, for example, it won't work because it will just be using the default identity for comparing objects. So we need to add equals and hash code, and while we're at it, we're probably going to want toString. So I've presented this before, and usually what I say at this point is you probably can't read this code, but you don't need to. And of course, here on this huge screen, you can read all that code. But the point is, anyway, that you have a huge amount of boilerplate code that is essentially the same for every value class, where you have to spell out equals is I compare all of the properties, and hash code is I hash up all of the properties, and toString is I append all the properties to a string. So that's kind of annoying. And if you look at it, a property like postcode there is referenced, the identifier postcode appears 11 times in that class. And if I want to add a new property, say country, I'm going to have to add that in the same 11 places. So that's really very annoying. So this is where AutoValue comes into the picture. And the idea is, instead of defining your concrete class address that has everything in it, you define an abstract class, and you have abstract methods for the properties of your class. So these are the same getter methods that you had before. The interface doesn't change from when you were writing this by hand. But now you have abstract methods for the properties. And what we're going to be doing here is the annotation processor is going to run during compilation, and it's going to generate a subclass of this, a sort of private subclass of this abstract class that implements those methods and that implements hash code and equals and toString in the obvious way. So it's going to write the code, the obvious code that you would have had to write. And so once we have that, you can just add a create method, and the create method is going to call. So this is the interesting part, I guess. It says return new AutoValue address. So that's the generated class. So the annotation processor is running, and it's going to generate this class AutoValue address. And you can reference it from your code, even though it wasn't there when you started your compilation, and that will work. So here's basically that's the subclass that it generates. So in a bit more detail, how does that work? You start your compilation with a set of input source files. So in this example, we've got foo.java and bar.java and address.java. And some of those source files might have annotations on them. And you might have your compiler set up in such a way that it runs annotation processors. So that's what we're doing here. As the compilation proceeds, the compiler is keeping track of what annotations has it seen. So after doing an initial phase of compilation where it's basically taking all of the input source files and compiling them enough to be able to see what the annotations are, it then hands over to any annotation processes that it found. If it saw an AutoValue annotation and the AutoValue processor says, oh, I'm interested in that kind of annotation, please call me if you see it. So the processor would then run, and in the case of AutoValue, what it does is it generates files. So with an input address.java, it's going to create AutoValue underscore address.java. So it's going to create that file. And then the next thing that's going to happen is there's a second round of compilation with all of any files that were generated during annotation processing after the first round. So the first round is the input source files that you gave to the compiler, and the second round is any new source files that were generated by annotation processing. And that can continue indefinitely. Well, not indefinitely. That can continue until Those generated things might themselves have annotations which could provoke further annotation processing. So you might have more than 2 rounds, but at some point you're no longer generating any new source code and you have all of your source code. When that happens, you have all of your input.java files plus all your generated .java files from all of the annotation processing. And that's when the compiler continues or finishes its work. It takes those sort of partially compiled things and finishes their compilation in order to generate class files, and then you get your complete program. That can work with Java-C being called from the command line, and it can also work in your IDE. This is the really interesting thing about annotation processing, is that it's well integrated with all 3 major Java IDEs. So they can basically, as you are writing your program, they can be running your annotation processor. So we will see that using NetBeans, which of course is the best IDE. And so here I have the same class that I was talking about there. And I'm going to add another property. And then when I save the file, you'll see a red line has appeared there because NetBeans has basically invoked the compiler, and it's discovered that this generated class here, so if we look at the error, it might even be legible on that screen, it's saying that that constructor hasn't got the right parameters because it's missing one, right? So I've just added a property, which means that the generated constructor now has that property, and my call to it here is incorrect. So I can fix that easily. I can do that. Oops. And then I can use code completion, right? NetBeans is smart enough to guess what the parameters are because they're all different types, so it just puts in the right values there for me, and suddenly it compiles again. I've just added a new value. And the IDE then allows me to visit that. If I do command-click here, it sends me into the generated code, and I can check that indeed the generated code is exactly what I would have written by hand, except I didn't have to write it by hand. So that's it for AutoValue. It's a very handy little tool. We're using it quite a lot in Google. There are like thousands of uses of it already, just because it saves you from doing this really obvious thing. It would be nice if Java had like Scala case classes or something, but this is a good alternative for as long as it doesn't. Okay, so I'll hand over to Christian, who's going to tell us about Dagger.
Thanks, Éamonn. Funny story is Dagger actually uses AutoValue in its processors, so it's turtles all the way down at Google. So Dagger is solving the problem of dependency injection. That's been solved before, but in particular, it's solving it in a slightly different way. Dagger originally was a Square and Google joint project. We did DaggerOne. It's kind of partially went down the road of compile time, code generation, and analysis. Dagger 2 pushes that a little further. Still a lot of collaboration, but primarily written by one of the audience members here, actually. And we're about to get to a developer preview with Dagger 2, and Jake Wharton is going to be giving a talk on Dagger 2 later. But I'm going to cover the basics a little bit. So what is dependency injection? Almost every one of you probably knows about it. It's really just decoupling built into a set of design practices. The major frameworks that you would have known about, Spring, Juice, etc., solve this using reflection. We decided to go a different way for a variety of reasons we'll talk about. But what is the fundamental problem? The fundamental problem is coupling. You want to decouple your code so that you have a variety of benefits, including testability, including the ability to swap in alternative implementations. If you look at mail server in this example, mail server owns the creation of and the lifecycle of its dependencies, and that's fundamentally the problem. You can't test mail server without accidentally testing all of its dependencies. You can't swap in alternatives. I've been in situations in clients where, for a lack of proper decoupling and separation, they started running integration tests and started processing credit card transactions in there, not in test accounts. And like it was pretty bad. These are horror stories that almost everyone knows better, but this is one of the techniques to get around that. Additionally, if you are using singletons, you end up with chains of static dependencies that goes all through your code. It's this big ball of mess. So fundamentally, dependency injection says it should own a reference to its dependencies, but it shouldn't own the dependencies lifecycle and creation. Something else should create those things and pass them in. And all it needs to do is declare, I need these things, and let some external agent be responsible for the wiring. Automated dependency injection, things like Spring, Dagger, and Guice, are simply ways of eliminating all the boilerplate associated with creating those manual injections externally. And in particular, as of the JSR 330, and Guice kind of started this approach a little bit, we use an annotation signal in order to do that. Well, if we've got annotations, we can do annotation processing. So what we've done with Dagger is we've gone all of the way with making the configuration language annotation driven as well. Guice already has some of that as well. You have provides methods in Guice, but you had types for modules. We just made that an annotation as well. And now we can scan all of this stuff because all of the configuration is declarative. You're not dealing with a runtime DSL. You're dealing with explicit declarations in the static structure of the code. So using those signals, we can actually generate code for a lot of the things that need to be done reflectively. All of the lookups, the analysis of the graph, including even generating pieces of code that do the work of constructing the instances, etc. Dagger has slightly deviated from sort of the historical dependency injection, which is about having a container or an injector or something that is the sort of God object that manages all of the graph. Instead, we went down the road of saying, well, why doesn't the user supply the entry points of the graph? And much like AutoValue, we will generate a backing implementation that does all of that hard work for you. So that's essentially what we've done. The result is, as of Dagger 2, completely all pure Java code. You can step through, you can F4 or command click your way through all of the code. You're not lost in reflection, stack traces, and et cetera. And you have an ability to do step-through debugging that you don't really get anywhere near as conveniently in a reflection environment. So why did we bother to go down this road? There were a few reasons. On the Square side, I believe a lot of it was performance on Android of Guice, because reflection is very expensive in Dalvik. From the Google side, we came to it because we wanted to simplify the APIs. We wanted to make it so that people were shooting themselves in the foot less with all of the tangle of configuration you can make with respect to Guice, and the ability to get your errors early as opposed to finding out a week later that some corner case weird configuration that was conditional that only happens on a code path, very specific data, and you find out your servers crash a week after you've deployed them. We don't like that. We'd like to find all our errors at compile time where possible. Additionally, that developer productivity is increased when you get your errors early. So that's where we went. So I'll just show you a little bit of what I mean by all of this. So we have a very simple little mail server here. And I mean, it's completely a contrived example, but it'll show you the process. So what we have is a mail service, and that mail service has takes a message and then outputs the message. And the message is injected. You would normally not inject things like this, but this is, again, a contrived example. And so the main just creates the actual component, and the component is the equivalent of the injector. It's the thing that's doing the injection, and that wires up all of this. It wires up this injectable class. And how does it do that? Well, we have a component. So we've defined a component here. It's just an interface. By defining component here, we have the annotation processor scanning all of these methods, and it looks for the types of the methods, the return types. In this case, mail service. So now it knows I have to go and create a mail service. How do I know how to create a mail service? Well, it inspects and says, oh, mail service has an @inject constructor. So I know how to build @inject constructors, so I will create a provider for that, and I will wire it up. And all of this is analysis done in the annotation processor. If there is a problem, then we get the errors. And it is generating all of the code over here. In particular, there's a factory for the mail service itself, and then there's a factory for the message. And how does it get the message? Well, it gets the message because we have made, hang on, let me go back. We have made a module, and in the module there's a provides method which provides a string. And that string just returns yay. Again, contrived example. So these are the different pieces that need to be wired together. And if you were going to manually do that, you would have a little class, and what it would do is it would, when invoked, it would construct the mail service, and it would construct the string, and it would put them in, and all of that would happen. And that's exactly what happens inside the component. The component is literally built as the code that you would have written yourself in order to assemble all of these pieces. What happens if you get it wrong? Well, let's say we want to, let's say we have omitted the message. So we forgot to configure something. Well, suddenly we get an error. And we get an error that's specifically, oh, mail service needs a string, and there is no string in the graph. I have no knowledge of string in the graph, and string is not a type that I can auto-create because it has no @inject constructor. So you either need to fix it and put an @inject constructor, or you need to provide a provides method, a way of hooking in things into the graph. So the configuration is very similar to Juice, but we're doing this all at compile time, and we're getting the errors instantly back in the IDE. These are graph wiring errors that you would normally see at runtime. Obviously, real examples are much more complex, but we wanted to keep it simple for the demo. Oops.
Okay, so well, I did promise that we would tell you how to write your own annotation processor. So we have a number of tips to allow you to do that. First of all, we need to establish what exactly you can do in an annotation processor and what you can't do. So a standard annotation processor using just the JavaX whatever APIs that are defined can see the overall structure of your program. Basically, it can see everything except the code of your program. So it can see your classes, what they inherit from, what type parameters they have, what their methods are, what the methods return, what the parameters are, what the fields are, but they cannot see inside a method to see what all of the individual statements inside the method are. So you can still do an awful lot with that amount of information, and in particular, AutoValue and Dagger are just fine with those limitations. AutoValue just needs to be able to see those abstract methods in your class so that it can implement them, and likewise, Dagger needs to be able to see the contents of interfaces, as we saw. So what can processors do? So it's general code. You can do whatever you like. It's Java code, but if you want to, for example, if you want to generate files, you really want to do that using the interfaces that are provided to you so that you're doing it in a way that is consistent with the compiler, so that it will do the right thing when it's Javac, which expects to put its files in wherever you specify it using the -d or whatever. If you're using the Eclipse compiler, it does the appropriate thing there too. So you can generate files, and typically you will generate, say, XML files or YAML files, or meta-inf services is a good example. So I didn't mention, but AutoValue is actually part of a suite of projects. There's a project Auto, which has basically AutoValue, AutoFactory, AutoService. We won't go into the details of those other ones, but AutoService, for example, is a very simple annotation processor that generates meta-inf services. So it just generates a text file. So anyway, annotation processors can generate text files, and they can generate any other files, but in particular they can generate, as we saw earlier, they can generate source files, and that's where you get the thing where you generate a .java file and it ends up being compiled alongside the original Java files in order to produce the complete program. So you can do all of those things, and the other thing that you can do that we saw in both examples is that the annotation processor can emit errors. So, for example, in the Dagger case, we saw that Dagger was running, the Dagger annotation processor was running, it was doing its analysis, and it was saying, oh, this isn't right because we don't have a thing that provides string, so here's an error. And you also saw in the IDE that you can say exactly where the error is. So the IDE is underlining in red exactly the thing that is the problem. So that works really neatly. So the things that processors cannot do, the main constraint is that they can't modify the code of existing classes. So that's a deliberate decision that was made during the design of annotation processors, with the thinking that it would be very hard to understand what a class actually meant if the code that finally ended up being produced was not the code that you saw in front of you. So if you look at something like AutoValue, it's generating a new subclass, but it's not touching the original abstract class. So you have this distinction between the input source code, which is inviolate, and the generated source code, which you can do whatever you like in. So that extends to you can't. It's a bit unfortunate. One thing that you really like to do in annotation processors would be to insert a new inner class inside an existing class. Even that you can't do. So that is one of the most important constraints. Okay, so we talk about annotation processors. That's the term of art, but in reality, this talk is called Plugging into the Java Compiler because it's really a general compiler plugin. It doesn't actually have to have anything to do with annotations. There's a way to say, I want this processor, annotation processor, to run on all of the source code, regardless of whether it has annotations or whatever. So you can have something that looks at all of your source classes, even if there are no annotations inside. Okay, so a reminder about defining an annotation. You probably know this too. So this is the syntax, but what's interesting here is if you've defined an annotation before and you've never used annotation processors, you've probably wondered, why is there such a thing as source retention? There are three kinds of retention. There is source retention, class retention, and runtime retention. And you can understand class and runtime retention, but why is there source retention? I mean, if I define an annotation that disappears as soon as compilation is finished, what's the point? Apart from the predefined annotations that the compiler itself understands. So the point is that annotation processors are still running during compilation, so they can see source annotations. So AutoValue, for example, is a source annotation, a source annotation, meaning that the generated code has no trace of the fact that it was generated using AutoValue, because your address class that has at AutoValue on it, if you do reflection on that, or even if you look at the .class file, there's no trace of that. But the presence of the source annotation was enough to tell the compiler, oh, this is an AutoValue class. Do your thing, invoke the annotation processor so it can generate the code. Okay, so an outline of what a processor looks like. The annotation processing API, it's quite a big API, but if you know what are the important points to start from, it's easy enough to find your way around. So an annotation processor, basically this is the outline. Typically, you're going to use the auto service project because, of course, you're going to love Google Auto. So you're specifically going to say AutoServiceProcessor.class, and that is going to mean that when you generate a jar out of this, it's going to have the meta-inf services blah blah entry that is enough to tell the compiler there's an annotation processor in this jar. Please run it when you do the compilation. And then your processor is going to extend abstract processor. So there's an interface processor and an implementation abstract processor. You would pretty much always extend abstract processor, and then that allows you to do a couple of things. First of all, it allows you to say what your supported annotation types are. So in the case of AutoValue processor, it's going to say, I support the AutoValue annotation. And the point of that is that the compiler won't bother calling your annotation processor if the annotation in question isn't there. The second thing that you can say is, what source version do I support? So you really have two choices there, and it's kind of a decision about, are you prepared to make a bet about the future of the language? One thing you can say is, I'm pretty confident that the sort of thing that I do in my annotation processor will still be valid in future versions of the language. So Java 9 and Java 10 are going to come up, and they're going to have modules or whatever, and I'm confident that my annotation processor will still work sensibly, or that at least it will fail in understandable ways. Or you can say, I'm not confident about that. I don't know what the future of the language is. So therefore, I'm only going to support a source version of, say, 8. So I know what Java 8 looks like, so I know my processor can work with that, but I don't know what 9 and 10 are going to look like, so I'm going to refuse to run if the compiler has minus source 9 or 10. Okay, so those are the things that you declare to the compiler, essentially, about yourself in a processor, and then the compiler will invoke this process method when it's doing an annotation processing round. So as we saw, you have your initial compilation of the input set of files, and then you have an annotation processing round where each annotation processor basically in turn is called with information about what was seen during that initial compilation. So the important thing, what you nearly always do is basically these lines here, and I'll talk a little bit more about some of them. But you want to use the second parameter to your process method, which is a round environment, and you're going to ask it, what are the elements that were annotated with, say, AutoValue? So it's the compiler is called my AutoValue processor, say, or whatever, and I'm asking you, which are the elements, which are the classes that had AutoValue on them? And then you call some method on all of those classes. You do whatever it is that you need to do, and then you return false. And we'll talk about returning false in a moment. So there is this notion, I don't really want to dwell on it, but there is this notion of claiming annotations where you can basically say, okay, I've handled this annotation. Don't bother calling any other processor for this annotation. So that's what the return value from the process method means. If you return true, you're saying, okay, I've done this. No other processor has the right to look at this. We're pretty sure that you never want to do that. We're pretty sure that you'll always want to return false because you really don't know what those other processors are going to be doing. And so how can you be deciding unilaterally that they can't? Okay, so one thing that there's a few little parts of the API that if you're coming to it for the first time and you haven't been given tips, you might spend some time discovering. So one of them that's important is that there's a package, JavaX lang model util, I think, with it's even there, with types and elements in it. So these are two basically utility. They're actually interfaces. They're utility interfaces, and you often find I want to know how to do this thing on a type, and I look at the interface for a type, one of the interfaces for a type, and I don't see it there. So the first thing your reflex should be, oh, what about types? So it's going to provide, so for example, if you want to compare two types to see if they're the same, there's a method in types to do that. There isn't one in type, the equals method, or type mirror. The equals method doesn't do what you expect. And likewise with program elements, so things like classes and methods and parameters and so on, there are methods in the elements interface that allow you to operate on those. And here's how you actually get an instance of those using those two methods, processing env.get something utils. And then another thing that nearly everybody writing an annotation processor for the first time, if they haven't seen this, ends up reinventing it because they don't discover it. It's kind of hidden very cunningly inside like a whole bunch of other classes with similar names, but it's really important. It's element filter, and it's really simple. All it does is you give it a collection of, say, some kind of element, and it returns the elements of that collection that, the members of that collection that are, in this case, types. So you can say, what are, given these elements, which are the ones that are methods, or which are the ones that are types? So in our case, with my annotation, or indeed with AutoValue, we want to know which elements among the collection of things that are given to us are actually types. And in fact, since AutoValue only applies to types, they can only ever be types, but the API signature is such that you're given this thing that is just element, and it's a pain to have to cast, and this allows you to avoid having to cast. Okay. So another thing that's a little bit head-scratching is that you have these things called type mirror and type element. The distinction is kind of subtle. It's similar to the distinction between, let's say, if you have a list of E versus a list of string. So a list of E is kind of the the type, the kind of template, and the list of string is the actual thing that is an instance of that type. So type element is like the list of E, and type mirror is like the list of string. But anyway, in practice, you don't really have to think about that too much. You just look at what the API gives you. If it's what you want, then that's fine. If it's not, then you can convert it into the other one. And there's a couple of ways to do that, which are shown here. OK, so did you want to talk about this? I think.
Sure. So one thing that you run into problems with often with annotation processors is you will have partial or incomplete or erroneous upstream compilation. So you have a source and you're processing it, but somebody missed an import statement, or they put in a typo into a class literal or something. You will start getting null pointer exceptions and class cast exceptions, really weird things like string cannot be cast into this internal Sun type. Very confusing stuff. That is almost always upstream compilation problems that has caused a bum AST to be given to you, essentially. So there's a bunch of different ways you can do it. The sort of poor man's way is to just trap class cast exceptions, but we've found it's much better to pre-validate the upstream AST or the AST produced. Essentially, when you get a list of elements that you're about to process, check them out and make sure they're actually valid. We've built a nice little utility to do that called Superficial Validator. It'll scan through and make sure that the bits and pieces are where they should be before you do the processing. In particular, though, it's worth pointing out that if you decide that the elements are not valid and you want to skip processing, an important little note is that you will never see those elements again. They don't come back in subsequent rounds. So if you know you're going to skip, you need to store the names of those elements that you're going to get again somewhere in the processor, because the processor instance persists across rounds. And then in subsequent rounds, you want to check, hey, are there any processing elements that I've skipped so I can reprocess them? So a few other gotchas. Type mirrors equals method does not work quite so well, or at least not how you would think. So you want to use types is same type if you're going to use the types utility. We also have some utilities that we've made in order to allow us to have static methods, so you don't have to constantly go to the processor environment and look up the types and elements utilities. So we have some of those tools as well. In the Auto project, one of the sub-projects is a little common utilities project, so very useful. Also, you're very often going to be doing instance of checks because you're going to see a type mirror, but is it a declared type, or is it an executable type, or what subtype is it? You don't want to be doing instance of checks and casting. It'll always go badly for you. So you want to use something like as declared, which is a nice little casting thing. It uses a visitor to check that things are right or throw a proper exception. Also, element filter is where that fits in if you're dealing with sets of these things. Although that's for elements. This is for type mirrors. That brings me to AutoCommon, which is essentially just stuff that we found very useful in the process of building our annotation processors that we've pulled into a little utility that we've made public. In particular, more types and more elements are just utilities for dealing with those particular ones of types, type mirrors and type elements, or elements in general. A particularly important thing is because hashcode equals, etc., are not necessarily going to be particularly helpful to you, what we found is for most of these types, we've used Guava's equivalence wrappers in order to provide a way to conveniently port things around and throw them in collections or use them in keys, etc. Because these equivalence wrappers will properly look at the contents and make sure that this type mirror actually is the same in meaning as this type mirror. So you probably want to use those. Superficial validation I mentioned. We have a couple of upcoming ones that are currently part of Dagger called annotation mirrors and annotation values. Very similar. There are just gotchas with respect to these where they don't behave the way you would normally expect value objects to work. Equals doesn't work the same way as you expect, etc. And so we have equivalence wrappers for those. Other static utilities. You can do everything that you need without AutoCommon. It's just you will often have to go and look up these things from the processor environment, the types utility and the elements utility. So the only real major thing that we changed is we just made static equivalents and did a little bit of work to avoid having to find these instances. So there's also this thing called JavaWriter. It started at Square as part of the Dagger project. I think Jake, who's sitting here, wrote a good chunk of it, the first version. And it builds up your class programmatically. We've gone a little bit further and turned it into much more of a class builder. And we're going to talk about other ways of generating code, but this is one way that we do it in Dagger. Essentially, you're just assembling the pieces, parts of code that you're going to generate, and then when you're ready, it spits out the actual string content, having taken care of things like what's your imports and shortening type names where we know that you're going to import it. You don't have to use the fully qualified name, so you can actually get nicer generated code that's a little more readable. This snippet is kind of gross in that it looks like a lot of work to do a very trivial thing, but you find that this becomes very, very powerful when you have very complex code that has, to insert the same kinds of things at different parts of the code. When you're doing them in a tight loop, maintaining little templates can be a bit problematic. So we found it very useful. The example I gave you gives you this very clean, obvious, readable code. The pros, programmatic, so where you have lots of tight loops and you're doing a lot of repetitive work, you can build up a code chunk and then export it nicely. You also get cross-referencing of things, so if you're referring to a symbol in 6 different places, you can refer to it with a programmatic element in JavaWriter. You don't have to pretend like it's a string. And it'll do nice deduplication. So if you have 2 things that you wanted to name foo, and it knows that they're 2 separate things, it'll name one foo and the other foo0 and take care of that for you. The downside, of course, is that the code that you're using to generate the code looks very, very different than the code that's being generated. There's no synchronicity like you get with templates. And that actually leads to Éamonn, who's going to talk about templates.
So I'm a big fan of templates, and it's really, I suppose it's a failing on my part, but I find that it's very confusing when you're basically using the same language to describe both how to generate the code and what the generated code is. So you've got Java that's doing the generation, and you've got the Java that's the generated code, and I don't know, somewhere in my mind this gets very hard to separate these 2 things. So I think it's nice to have a completely different syntax, a completely different way of expressing the things that are really template logic and the things that are the generated code. So that's what we're seeing here, and this is actually an extract from the template that AutoValue uses. So this is using Apache Velocity, which is a well-established template engine. And without going into the details, we can see quite easily where the code extract at the bottom comes from by looking at the template. So the template is looking at each of the properties in the address thing. So it's got the street address and the postcode and so on. It's going to iterate over all of those in a for each loop. And it's define P as the property in question, and everywhere then we're going to be able to look at the values that we have associated with that property. So essentially there's 2 phases to this. One is the annotation processor is basically going to be building up the variables that it's injecting into the template. So in this case P, but there's a bunch of other ones too. And then it's going to be invoking the template engine to get the generated code out at the far end. So I would say there's really only, Christian gave a list of pros and cons for the programmatic approach using JavaWriter or equivalent. And there's a long list of pros and only 1 con. And I would say that for templates, it's the opposite. There's only 1 pro and a bunch of cons, which are the opposite of his pros. But I think that the pro is the big advantage of templates is sufficient to outweigh the fact that it does have these drawbacks compared to code generation using programs. Okay, so Apache Velocity, I was saying that's the engine that I use, and the reason for that is really that it's well established, it's reasonably stable, and in particular, it's supported in IDEs. So that's important. The syntax highlighting that I'm showing here is basically copied from. That's exactly the way that NetBeans displays it. So it's much easier to see, just using the colors, it's easy to see what is the stuff that is like the logic for the template and what is the actual literal code that's being generated. Right, I mean, just got $P is in green and equals is in black. That immediately shows you which is which. I do have to say, though, that if you care about what the generated code looks like, you're probably going to need to do a post-processing step because you get a lot of extra blank lines and spaces and stuff. So that's what I do in AutoValue. Okay, I think back to question about testing.
Yeah, so there's obviously everybody here would be familiar with the different kinds of testing, unit testing, integration testing, etc. The unit testing annotation processors, because they happen during the lifetime of the compilation job, in the middle of a Java C run, it can kind of be a pain, because especially when you have the need to get the types utils and the elements utils, because those particular utils are instances of interfaces, and you don't have access to the implementation. So you can't just randomly say, hey, I want an element, because you don't have anything running to generate the element. You need a Java compilation run. So you can spin up an OEM version of the compiler yourself and do all sorts of things like that. We've made it a little bit convenient. We have a project called Compile Testing. The author of that's in the room. And one piece of that is a nice little Java rule that you can run that will spin up the compilation and then give you access to some other things as you need to, in particular to set up test data. For succeeding integration tests, of course, you can just run your processor on your test code and make sure that the actual results work the way you expect. That's easy. But failing tests is actually a pain, because you don't want to fail the build that you're actually running the test in. You want to fail the build that would be running in the real case. So we also have part of the compile testing is an extension to the truth assertion library, which lets you make assertions about compilation runs, essentially. You assert that this group of sources, when processed by this particular stuff, either fails or succeeds. If it succeeds, it generates these code elements. If it fails, it has these errors. You have all sorts of assertions that are built in that let you conveniently do that. Yeah, just a simple example. We have a bit of source that we've generated, so you can make source out of strings. In memory, it's very quick, or you can load sources from files, from template files if you want, or test data. Then you assert that the immutable set of these files processed with a particular processor, in this case, fails to compile and has an error containing this text on this line. So you can actually get right down to where is the error showing up, which is important. If you're writing an annotation processor, you don't want to just throw an error. You want to throw an error and associate it with a program element so it shows up in the right place in the IDE. You can actually test that your processor did the right thing here, even outside of an IDE. As I said, succeeding integration tests, you can always just run the code. So run the processor on your test code, which then generates results and runs successfully, and then you win. You can also do golden file tests, particularly for generated code. You want to know that your processor generated code the way you expected, and you can certainly do that with the compile testing extension to truth. You want to be a little careful because golden test files are brittle. In Dagger 2, we kind of got a little happy with our tool, so we over-tested with goldens, and we're going to back out of that, put more proper functional tests in. There's nothing technically wrong with it. It just means you make a change to your processor, and you got to change 1 million golden files. You need to find the balance for your project, obviously. Yeah, this is my rules of thumb. Bulk of your use cases should be functional. Test a few goldens to make sure that the processor output looks the way you expect, but don't overdo it. Test your expected errors, and unit test as much as you can in the process.
Okay. So that's about all we had. So just to remind you of everything that we saw, annotation processors allow you to plug into the compiler. They're a powerful way to extend the compiler. There's an ecosystem evolving around them, so IDEs now support them well. There's a bunch of existing annotation processors out there, including the ones that we've talked about. So you can look at those to see how things are done. There's a bunch of projects that support you in creating annotation processors, like JavaWriter and compile testing and so on. And there are a bunch of important advantages to annotation processors that we've seen. The early error checking, the fact that you actually see the errors in your IDE, that's just golden. Performance improvements, like what we saw with Dagger, the fact that a lot of stuff is being done actually at compile time rather than at using reflection at runtime. And you can see the source code that's being generated, and that makes it a lot easier to understand. It's a big difference. We haven't really been talking about Dagger versus Juice for people who are familiar with Juice, but the fact that it's generated code makes it much, much easier to see what's going on. When you have a lot of reflection going on in frameworks that use a lot of reflection, which is often the alternative to using annotation processors, it can be really hard to figure out what's going on because everything is so indirect and is contained in the runtime state of your program. So generated source code is for the win. Okay, and here's a bunch of resources, basically things that we talked about. So that's it. If there are questions, we'd be happy to answer them.
Although it's hard to see. Yes?
In your example about the address, you had a field called country. Do you clone the country in your constructor, or what do you do with it?
Okay, so I have to repeat the question because for the recording. So the question is, when I did the example with address, I added a field called country. Do I need to clone that to make my instance? So typically, when you have a value type, you want it to be immutable, and you want the types of its properties to be immutable. So in the case of country, I mean, the actual one that I used for the demo was an enum. I think you're in a delicate situation if you want to use a mutable type as contained within an immutable type.
They also have an example with the int array.
Yes.
So there you do cloning.
Yes. So we, as a sort of concession to performance, we did allow you to have primitive arrays only, not other kinds of arrays, because there's no real reason to support them. Right? You can just use a list instead. But we do support primitive arrays, like so you can have a byte array or whatever. And in that case, the AutoValue will in fact clone the array in the constructor. Sorry, no. What it will do is you can clone the array in your static factory method, and then the getter for the array will clone it, so that you can't modify the value by modifying the returned array. Other questions?
Yes.
Oh.
The field you added is added at the end of the parameter list, but later versions of the class files contain fields in a more or less random order. How does that translate to the syntax tree? Is that still in source order?
Yeah.
So that's a very interesting question. I guess, so to repeat the question, so if I understand it correctly, with AutoValue, we saw that the constructor parameters basically corresponded to the methods in our class. And you're probably thinking of reflection, where in Java 6, I think it was, they basically changed things so that the order of methods that you get from reflection is no longer really predictable. It wasn't entirely predictable before, but it's now completely unpredictable. But we're still at the source level. So the compiler actually does have the information about what order the methods and fields were in. Yeah. Unfortunately, there's a bug in Eclipse where it doesn't follow that spec, so it actually sorts the methods into alphabetical order for no very good reason that I can ascertain. But it's a huge pain. I actually had to spend a lot of time with AutoValue to basically reparse the source code and establish what was the original order before Eclipse got its hands on the source code.
But the get enclosed elements method ought to be returning in the order of declaration.
Yes. Yes.
Yeah.
Other questions? Yes?
You mentioned that annotation processors can only generate code, not alter existing code. But I wonder how a library called Google
We get this question every time.
Yes. We
shall I?
sort of knew that somebody was going to ask this question. Do you want to take it?
Yeah, the question is, what about Lombok? In particular, we have made the claim that annotation processing environment does not allow you to modify source code or modify code under compilation. The APIs of the annotation processing environment in the JSR does not permit that. The internal types that JavaC uses to implement those APIs completely has access to these because it just has wrapped these APIs around the types it uses in its own compilation, and it can modify whatever it wants. It's JavaC. So what many processors do is they cast into the internal types of the processor because they happen to know that these are the implementations, and then they use the additional APIs that are associated with those internal utilities in order to do these modifications. So we consider that a problematic approach, but that's the decision that we made for our particular things. It is certainly a powerful thing you can do. What it does mean is that you are then tied to making bridge code between you and every different implementation. So if a subsequent JavaC is released that has changes to those internal types, you're going to have to rewrite or write bridge code to make sure that your behavior is mapping to the new APIs. And I believe Lombok has bridge code to JavaC of various versions, to ECG, etc. You can do it. It's an additional maintenance burden, and it's not really the purpose of the APIs that we're talking about. It's kind of going past those APIs deeper into the internals. So.
Right. Now I mentioned that it was a deliberate design decision of annotation processors not to support modifying code for what I think were good reasons. I mean, they felt the spirit of the Java language is that it's straightforward. What you see is what you get. There are no macros or operation overloading or whatever.
Yeah.
So operator overloading. I mean, so it's kind of going against the spirit of the language to do that sort of thing. Apart from the fact that it's a huge maintenance nightmare, and I think Lombok in particular has had a lot of difficulty keeping up with different versions of Java and different versions of Eclipse, JavaC, I should say. Other questions? Go ahead.
Yes.
You said you can process anything, even if it's not annotated. I think the code snippet you showed got a set of annotated elements or something.
Oh, yes. Okay, so the question is, we said that you can process anything even if it is not annotated, but our code snippets were very much focused on annotations. That is true. But if you, in the one code snippet we gave about the declaration, if you declare, I accept anything, not just a particular set of annotations, then you can't go, you can't reasonably use the round environment get things annotated with this, but instead you can actually get all of the root elements. There's other APIs in the code that let you get the set of root elements, and then you can inspect everything you want. Or you can use the types and the elements utilities to get arbitrary elements by name. And so if you have things that you're going to look for, you can also scan and grab and create those instances as you need to, as long as it's in either the sources or in the class path that's provided. You can inspect it, analyze it, generate code off of it.
Okay. Any other questions?
One right here.
Oh.
What about build time in Guice? What was the strike with using annotations?
Performance costs of build time.
Will,
Yeah. We haven't done, so the question is, what about build time performance costs? So we have not done a lot of profiling. We also have very, very big projects, some of which make massive use, even indirectly, of this, because they use a lot of things that use AutoValue or Dagger, etc. And we so far have not had the people who would complaining at us that their build times are slowed down. We have some teams that are very sensitive to build time, and they haven't experienced this so far. That said, we have not done any serious profiling. I certainly could profile our annotation processors. We know about roughly what the work is. I don't know that we've ever done any profiling of the overhead of executing annotation processors itself, or what JavaC incurs in trying to run these things. But at this point, we have so many processors running that we more or less have turned processing on across all of Google builds. So whatever overhead we're getting across all of Google now. and we seem to be functioning fine with it. So on smaller code bases, I can't imagine you running into a problem.
Okay. I think that might be it.
Yeah.
No further
Oh,
questions?
there's a question way back
yes,
in the side.
yes. You need to shout.
Maybe you said it, maybe I missed it, but do other processors generate the code as well?
Yes, they do. The question is, do other processors see the code that you generate? Yes, that's why there's multiple rounds of processing. You generate code, and as long as code has been generated in the previous round, another round of processing will occur, and that will continue until no processors have generated any more code. So you can cycle for quite a while, and because we use processors that generate code that's annotated for other processors, we have like 3 or 4 layers in some cases of that, and all of that works just fine.
Okay.
Yeah, I think we're out of time.
I think we are out of time. So thank you very much.
Thank you very much. Yeah.